morning, students. The continuation of the last two classes, we will discuss today the property of Laplace transform, that is nothing but division by t method or Laplace integrals. So what is this method actually? So the statement is, if L of ft equal to fs, then L of ft by t equal to an independent integral s to infinity fs ds. So what is the proof? Proof is again very simple. So what is ft here? Ft is nothing but ft by t. So you just plot in the formula ft by t, and then you will have to s to infinity fs ds equal to s to s 0 to infinity t to t equal to 0 to the power minus st ft dt ds. Since s and t are independent variables, by interchanging the order of the integration, we will have s to infinity fs ds equal to t equal to 0 to infinity. Now just interchanging the values, s equal to s to infinity e to minus st ds ft t. That is, we just interchanging s and t. So integration from t equal to 0 to infinity e to the minus st by minus t into s equal to s to infinity ft dt. So we will finally have t equal to 0 to infinity e to the minus st by ft by t dt. Clearly, s to infinity fs ds equal to L of ft by t. Therefore, L of ft by t equal to s to infinity fs ds. So this is nothing but the division method for Laplace transform. So we will illustrate this method with the help of an example. So this example actually. If you are going to find L of e to the power minus at minus e to the power minus bt by t. So clearly it is of the type L of ft by t. So here ft equal to e to the power minus at minus e to the power minus bt. So clearly if you take both the Laplace in both sides of ft, so L of ft equal to, that is fs, equal to L of e to the power minus at minus e to the power minus. So we just use the formula for L of e to the power minus at is nothing but 1 by s plus a, and e to the power minus bt is nothing but 1 by s by t. Now the theorem tells us that L of ft by t equal to s to infinity fs ds. So L of ft by t equal to s to infinity. What is your fs? The fs is nothing but 1 by s plus a minus 1 by s plus a. So you just plot it over here, ds. Integration of ds by s plus a is log of s plus a minus ds by s plus b is log of s plus b. You put the upper limit and lower limit. If you simplify this, you will have that log of s plus a by s plus b. So the result of L of e to the power minus at minus e to the power minus bt by t is nothing but log of s plus a by s plus b. Simple. This is simple and simply a note for the division theorem. That is, if ft equal to fs, then L of 0 to t ft dt equal to 1 by s of s. So proofs are not required, but the direct result is given over here. Next we will come to the next theorem, that is multiplication of t. That is, what will happen if we are going to find out Laplace transform for a function of t when t is multiplied with the Laplace. So the statement is, if L of ft is fs, then L of t ft equal to minus the ds of fs. So proof is simple. You just plot in the definition. So take both sides dd's 0 to infinity ft and del s of e to the power minus st into dt. So you just use the partial derivative concept to get the value as minus L of t ft. Okay, because in the final line you will have minus 0 to infinity e to the power minus st into ft dt. What is your ft? Ft is nothing but t of f. You just plot it over here. So finally you will have L of t ft equal to minus t f by ds. That is the ordinary derivative of s f with respect to s. So what is the generalization of this multiplication of the theorem? That L of t to the power n ft equal to minus dn by dsn into fs. So again an example is taken to illustrate the formula. If what will happen if you are going to find L of t into sin a t. So what you have, we know that L of t ft equal to minus d of ts. So here ft equal to sine of at, that is he ft. So L of ft equal to L of sine at is 1 a by s square plus s square. So therefore L of t sine at equal to minus the ds of what is your f fs. Fs is made by a by s square plus s square. Now take the derivative of a by s square plus s square with respect to s. We will have twice as by s square plus s square. So that is nothing but the value of L of t into sine a. So with this we will conclude the part for Laplace. A few properties starting from the definition, introduction to what usefulness, advantages. Then after discussing the properties with various examples, we will move towards the next part of our content, that is nothing but inverse Laplace transformation. Okay, so what is the definition of inverse Laplace? It is just nothing but the inverse of Laplace. That is, if ft equal to fs, then ft is known as the inverse Laplace transform of fs, and it is denoted by L inverse of fs equal to f, where L inverse is known as the inverse Laplace transform operator, and is such that L into L inverse equal to L inverse into L equal to 1. Okay. So here some formulas, transformations for some elementary functions are given. That is L inverse of 1 by s equal to 1, L inverse of 1 by s minus a equal to e to the power at, L inverse of 1 by s to the power n equal to e to the power n minus 1 factorial n minus 1. In this way, we will give some elementary transformations for some elementary functions. Now, how could you use the concept of inverse Laplace transform in a problem based on partial fractions? So partial fractions, all of you know, a fraction of the form, this is numerical denominator, in which both powers m and n are positive numbers, is called the rational algebraic function. Okay, so from the definition of algebra, to resolve proper fractions into partial fractions, we first factorize the denominator into real factors. That means to make a particular function in the partial fraction form, what you have to do first, we have to factorize the denominator into some real factors. So this will be either linear or quadratic, and some factors may be repeated. So from the definitions of algebra, a proper fraction can be resolved into the sum of the partial fractions. So this is the table which shows the factor of the denominator and the corresponding partial fractions of that. So first one is what non-repeated linear factor, that is 1 by s minus a, that is s minus a occurs only one time. So in this function in partial fraction form, it is obtained at a by s minus a. So when the word factor is repeated suppose r time, that is s minus a to the power r. So the corresponding partial fraction should be a1 by s minus a plus a2 by s minus a square plus ar by s minus a to the power. Now the third type is if the factor of the denominator is non-repeated quadratic expression like s square plus a square, then what will the partial fraction corresponding as plus b by s square plus a square, where a and b cannot be the same. The last one is for repeated quadratic expressions, repeated r time. So in partial fraction form, it should be a1s plus b1 by s square plus s plus b. So since it is repeating, so square term is increasing. So next term is what? a2s plus b2 by s square plus as plus b whole square. In this way, it will be generalized. So we already discussed the shifting property in Laplace transform. So it is shifting property of inverse Laplace transform is just nothing but the inverse of the shifting property of Laplace transform. So what will be here? So what we know that L of e to the power at ft equal to f of s minus a. We just move that L to the right hand side to get L inverse of f of s minus a equal to e to the power at. This is nothing but the shifting property. Okay. So there are some basic formulas are also given, that if L of n is L inverse of Fs equal to Ft, then L inverse of f of s minus a, that is known as the shifting property, it is equal to e to the power Ft, sorry. So similarly other formulas are also given. So these formulas we will able to use while solving problems, and as well as problems for what application based differential equation problems. Next, another important main part that I mean to say, the main part of inverse Laplace transform is nothing but the convolution theorem. Okay, so when a differential equation can be converted into Laplace transformation, in this the denominator should contain at least two terms. Convolution is used to find inverse Laplace transform in solving differential equations and integral equations. So what is the main statement of the convolution theorem? So what is the statement? Suppose we will take two Laplace transformations, Fs and Gs. Fs is equal to L of Ft and Gs equal to L of Gt. So what is given here? Here let Ft and Gt are the inverse Laplace transforms separately, such that L inverse of Fs equal to Ft and L inverse of Gs equal to Gt. Okay. Then L inverse of Fsgs, that is the proof. L inverse of Fsgs equal to, the result of the convolution theorem is 0 to t fu g of t minus g, that is f and g. So that small fu will come from the function f of t, that is t is replaced by u, and the small function gt minus u is replaced by gt, that is we just replace t by t minus u. So here f star g is called the convolution or faulting of f of g. So proof is not required. So we will that is I just repeat the convolution theorem for inverse Laplace. If L inverse of Fs equal to Ft and L inverse of Gs equal to Gt, then what will happen if we take the product of both two functions, that is L inverse of Fs into Gs, it is nothing but 0 to s equal to 0 to infinity e to the power 0 to infinity then 0 to t, sorry, fu g of t minus ut. So to illustrate the statement of the convolution theorem, we want to evaluate L inverse of s by s plus s square whole square. So here in L inverse there are two factors, different factors are multiplying. One is s by s square plus s square dot 1 by s square plus s square. So we need to what? We need to find out separately L inverse of s by s square plus s square, which is nothing but 1 by a sin 80, and L inverse of 1 by s square plus s square is equal to nothing but 1 by a. Here is sin au, because gt minus u is given. Sorry, f of u. We need f of u. So f of t already find out 1 by a sin 80. So what is your f of u? F of u is nothing but equal to 1 by a sin 80. Next, similar cases will arise for gt, and gt equal to L inverse of gs, so L inverse of s by s square plus s square, which is nothing but cos of 30. So by convolution theorem, now we are going to use 0 to t or 0 to u, f of u g of t minus a du. So you just plot it over here, 1 by a sin au cos a t minus u du. We will use some simple trigonometric transformations, such that u equal to 0 to t twice sin au cos a t minus a du and multiplied by 1 by twice. Now if you just simplify this, you will have the value, you will what, 1 by twice a equal to u equal to 0 to t sin a t into du plus 1 by twice a, this result will come. So finally we will have 1 by twice a sin a t, u at t, upper limit is t, lower limit is 0. Finally we will have 1 by a t sin a t. That is the value of L inverse of s by s square plus s square whole square. So this is a small concept about inverse Laplace transform. So next class we will discuss the application of differential equation by using Laplace and inverse Laplace transform.